At this point, I assume that you're pretty familiar with things like malloc and free. So today, we're going to do a quick review of dynamic memory allocation, and then we're going to focus on a couple of characteristics of memory allocation that you might not be aware of or may never have really thought about. You're probably already aware that C has different kinds of variables, or different kinds of memory. What I mean by this are not the types like integers and longs or shorts. What I mean are where variables are allocated and also how long they live. So here's a quick summary, and then there's also more detail on the website under the resources section. But we have global variables. Those are visible throughout your entire program, and there are two kinds of globals. You can have constants or variable variables, right? Constants, you can't change them. So they're typically placed in a read-only segment. Regular globals that aren't marked const, you can change, and so they will appear in a read-write segment. Then you have local variables. These are the variables that get created when you invoke a function and live on the stack. They are private to a particular function, and for the most part, they only live as long as that function is executing. And when the function returns, the variables sort of disappear. Now, there's a special kind of local variable called a static. You identify it with the static keyword that doesn't disappear when the function returns. And in fact, every time the function is invoked, a static variable continues to exist and you get the same instance of it. And therefore, it has to be allocated in a data segment. So if the static variable is initialized, it ends up in read-write data. If it's uninitialized, it ends up in a segment called BSS, which gets created when your process gets created. But today, mostly what we're going to talk about are dynamic memory locations. So these are accessible to any code that has a reference to them. By reference, we typically mean pointer. They're allocated out of a heap, and the program that uses these dynamic data structures is responsible for explicitly allocating and deallocating them in C. In other languages, you can dynamically allocate variables, and something like a garbage collector will clean them up. And that's something we'll talk about a little later. You might remember this picture from a few videos ago where we showed what a process address space looked like. Lower addresses are at the bottom, higher addresses are at the top, and in the middle is this segment called the heap. And I mentioned that the heap can actually grow while a program executes. So if you continually malloc space and never free it, then the process will actually continue to allocate memory until it reaches some limit. And that limit here is shown with the blue bar, which is not part of the address space. The way that processes can explicitly grow their heap is by using the sbreak system call. You can do a man on that and look for more information. But for the most part, most programs interact with the heap by calling malloc or its associated routines calloc and realloc and free. A reasonable question you might ask is, well, when should we use data from the heap? Like, when should we call malloc and free? And the short answer is, well, anytime that local or global variables don't really work. So for example, maybe you don't know at compile time how much space you'll need. You're trying to store data that you're getting from the user or from a file that you didn't know existed. So at that point, you can't possibly allocate it statically, so you might want to allocate it dynamically. The second case is if your data grows and shrinks. So you want to look at a bunch of stuff and then you get rid of it and throw it away and then you want a bunch more. Well, malloc and free will let you do that efficiently. Also, if the lifetime of the variable isn't well matched to any of the other types. So you need the data outside the context of one function, but in fact, it's not truly global, and we all know that we like to avoid global variables when we can. So those are some of the cases in which you might use dynamically allocated memory. By this time, I'm sure you've all used malloc, perhaps even calloc and realloc, but have you ever read the man page? If you do, you'll find this one statement that says the allocated memory is aligned such that it can be used for any data type. So what does that mean exactly? Well, it turns out that in C, each object has an associated alignment that basically restricts the memory addresses at which variables of that type can be allocated. So for example, a short, which is 16 bits or 2 bytes long, has an alignment of 2. And what that means is that anytime we allocate a short, it's going to be placed at an even address and will never be placed at an odd address. That is, it has 2-byte alignment. So you can generalize this and say that every type T has an alignment A, such that every single time you allocate a variable of type T, the address at which it's allocated is going to be a multiple of A. So during class, we'll want you to experiment and figure out what the alignment is of various types. But for the purposes of this presentation, what I want you to think about is if each type has an alignment, and when we allocate dynamic memory, the allocator has no idea what kind of data we're going to put in it, then the allocator has to make sure that whenever it gives you memory, you can put any variable in there, and therefore its alignment must be at least as great as the greatest alignment of any type you might use. So I've written a little program here designed to tell us what is the alignment that malloc returns. This is in the dynamic repository in the videos directory if you want to download it and follow along. The way it's going to work is I'm going to do a large number of allocations, in this case 100,000, and then for each allocation I'm going to look at the address that malloc returned, and I'm going to figure out which powers of 2 divide evenly into that and keep track of the maximum. So, if we assume that the alignment of this machine is bigger than 2 bytes, then we would expect that not only is every address generated by malloc divisible by 2, but it's also divisible by 4. And the question we're asking is, well, are they always divisible by 8 or 16 or 32? Like, what is the minimum allocation unit or the minimum alignment that malloc is going to give me? So the way I figure that out is, for each of these allocations, I'm going to generate a random number and I'm going to allocate that much memory. I'm going to modulo it by 1024 so I don't allocate too much memory. And then what I'm going to do is I'm going to iterate over all the powers of 2 between 0 and 2 to the 10th. And I'm going to try to keep track of the maximum value that is in fact evenly divisible, that this pointer is evenly divisible by, right? So I take the pointer P, and even though it's a pointer, I'm now going to cast it to a type called a uint pointer under T, which is an unsigned integer that's large enough to hold a pointer. And now I can do a mathematical operation on it. In this case, I'm going to take the modulo of size, where size is the power of 2 that I'm incrementing in each iteration of this loop. And I'm going to keep track of the maximum. Once I've computed the max, I will increment a histogram. And I just realized there are ways we could optimize this code, but that's left as an exercise to the reader. And then after I've done all these 100,000 allocations, I'm just going to print out my histogram. And what this should tell us is that all malloc memory is given to you at an address that is aligned on some boundary. And the question we'd like to know is, well, what boundary is it aligned on? So if we run this program, lo and behold, it's very clear what the alignment is on this machine. Right? Every single address that malloc generated was divisible by 16. Some of them were also divisible by 32 and 64, but all of them were divisible by 16. So what this tells us is that on this machine, the alignment that malloc returns is 16 bytes. Now that we've discussed alignment, I want to talk about a last topic called fragmentation. So I want you to consider the following workload. Let's imagine that as long as there's heap left, in other words, as long as malloc continues to return something as opposed to null, we malloc 2 pieces of information. So first a 256-byte piece of data and then a 128-byte piece of data. And we just keep repeating this until we fill the entire heap. The question I'd like you to think about is, what happens if we then free all the 128-byte objects? So once we do that, we know that roughly a third of memory is free. But what if we now call malloc and ask for a 256 byte object? What do you suppose will happen? Well, I hope you've all decided that malloc will actually fail. And the reason it'll fail is due to this concept of fragmentation. So if we draw a picture of memory, what we've done here is we've said, okay, here's a 256 byte chunk, and then here's 128, and then here's a 256 and 128 and a 256. So the dark ones are 256 and the light ones are 128. So we filled up all of memory this way. Okay, and now when I say we free all the 128, that means we're going to free all these pieces here. Okay, and the problem is that when I now ask you for 256 bytes of memory, you've got way more than 256 bytes available, but it's not arranged in a way that you can actually access it. Okay, and this is a problem. And this problem is what we call fragmentation. In particular, the scenario I explained on the last slide is what we call external fragmentation. So that's when we actually have enough free space to allocate something we want, but because of the algorithm that the allocator uses to allocate memory, we're actually unable to grant the allocation because the free space isn't arranged in the right way. Right? In the last slide, we had tons of memory, but it was broken up into these little pieces, and so we couldn't use it. So external fragmentation only happens when we permit variable size allocations, right? If all the allocations were the same size, we couldn't have this problem. So when I pose the question, how do you avoid external fragmentation? Well, there's at least one good answer, which is allow only fixed size allocations, right? Then we know you can't have external fragmentation because all the pieces are the same size. And so as soon as you free one, another one's available, that's available for the next allocation. So it turns out there's a whole class of allocators called fixed size allocators and slab allocators. And they take exactly this approach, which is if external fragmentation only happens with variable size, let's try to get rid of it. So there's a couple of different ways to think about this. One way is at the application level. You can sort of do your own allocation. You could allocate a big chunk of memory, and then you could allocate widgets inside that, all widgets being the same size. And now you have a fixed size allocator. Alternatively, there are systems that support things called slab allocators. So what they do is they allocate multiple different slabs, which is a big chunk of memory. And then when you request an allocation of a particular size, they put it in one slab. So they might say we have one slab that we allocate 16 byte structures and another one that we do 32 and maybe 64. And we keep going to larger and larger units. And when you request a chunk of allocation, we find the slab that has the smallest size greater than the allocation you want. And so this lets us do fixed size allocation within each slab, which is relatively efficient. Now, you might think that fixed size allocators get rid of all kinds of fragmentation. Unfortunately, fixed size allocators introduce just a different kind of fragmentation called internal fragmentation. Internal fragmentation occurs when you want a chunk of memory, but you're given a piece of memory that's larger. So let's imagine we had a slab allocator that allocates either 16, 32, or 64 byte chunks, and you requested 40 bytes. Well, what would happen is the allocator would give you a full 64, and your data would only consume about 2/3 of it. So this other space is wasted space, and that you've been given it, but you're not actually using it. So you can't avoid fragmentation completely, but you can design systems to try to minimize fragmentation. And so the exercise that we'll do in class will actually show you how much more efficient a fixed size allocator is when that's in fact what you need. Let's just wrap up with a couple of observations. Dynamic memory allocation is actually a critical component of almost every application. It is really important from a performance point of view, but it's also important from a memory efficiency point of view. In C, allocators are required to provide aligned storage, depending on the architecture. So different architectures will have different alignments. And different types of allocators will produce different kinds of fragmentation. You have external fragmentation when you have space available, but it's arranged in such a way that you can't use it. And you have internal fragmentation when you're given an allocation that's bigger than you wanted, so there's space in there that's being wasted.